Welcome back. So we are going to look at one of the most basic things about dynamical systems, that is the behavior, especially in the asymptotic times, in the long time. What happens to the dynamical systems is what is the focus of this particular series of lectures. So first we will go through the connection between flows and solutions. Then we will introduce this concept of limit points, limit sets, and attractors, and then finally we will look at very important behavior of periodic orbits and limit cycles. But first we will see it a very see all these concepts in a very generic fashion through some examples, and then we'll look at specific definitions and things like that. Now, but let's get back a little bit and then see where we are, right? We are now convinced that we want models that are of ordinary differential equations, linear or nonlinear. Now, if they are linear, then things are much simpler. We can have solutions that are relatively straightforward in terms of this matrix exponential, whereas when it comes to nonlinear systems, the guarantee of a solution is not always there. But if you have some nice conditions, x dot equals f of x, if f happens to be continuously differentiable, for example, you have existence and as well, right? Of course, that's not really necessary, and then you have something called Lipschitz continuity, and that's more than enough for guaranteeing existence and uniqueness. But of course, you have several levels of existence and uniqueness. The first one is basically you just get existence and uniqueness in local time and space, and then you can increase that a little bit, and then finally the best one is global existence in terms of that is basically if we start some ordinary differential equations at some initial condition, the solution is unique, and then it extends up to whatever time that you can think of, infinite essentially. And then such a result requires something called global Lipschitz continuity, which is essentially it's a Lipschitz continuous condition at every point with some kind of uniformity in terms of this Lipschitz constant. And then such a condition can be guaranteed by continuous differentiability everywhere with some bounded derivatives of this function f of x, right? And in some cases we cannot avoid the more let me use the word nasty conditions that do not guarantee us this existence of solutions throughout. Two things are possible. One, the model itself does not represent the real system, because in a typical real system we expect solutions to exist forever. The second thing is the system is so complicated that we chose to basically develop a model that is valid only locally, right? And then of course that becomes more difficult to figure out what should be the next model that we need to do, and then stitch all of them together and then decide something. But in most cases we can live with conditions like continuous differentiability and some kind of bounded derivative, and especially when we are trying to control the closed loop system. So-called closed loop system is going to have this condition, not a bad assumption, or we should aim for the closed loop system to have this particular condition, right? In that sense it's quite important. But otherwise, most of the time we can forget about these technical conditions and assume that the solutions exist. If somebody has done a good job in terms of picking the right model, then they will have these nice conditions, right? If they don't, then you have to go back to the basics and be extremely careful in terms of how to deal with those cases. So yes, now we understand that given a differential equation x dot equals f of x, again let me remind you, whenever I use that, this is a vector differential equation. We have seen how to go from higher order differential equations to this first order vector differential equation using this method called state space transformation. So all that is there. So we're going to assume we are going to always start with x dot is equal to f of x, and with some initial condition given, right. Now, what is that we want to do? Well, in typically a control system, we are interested in seeing this x reach some point, right. This x of t is going to go to some point and then remain at that particular point. Now, there are many examples. The standard simple examples that we can think of is if you are driving a car, we want to retain a particular speed, and then that speed reaching a particular point is essentially that, right. Of course, the more subtle point is basically we need not have the entire state x going to a particular number, but we actually want some output of this particular system go to a particular number. So anyway, for the time being, we will pick the simpler question of basically we want this x to go to some particular point, and then that is more than what we need most of the time, but sometimes that's easier to achieve if we have all the hardware available. And so what else can we expect from a control system? Sometimes we may not be able to go to a specific point, but we may actually go around a region, go to a region and stay there. All kinds of possibilities are there, but in all these things, basically we are trying to control some system. It will take some time, and then it will reach the desired behavior at the end. That desired behavior typically, hopefully, is a single point or a single set of well-defined points. So in all this, therefore, we are interested in ensuring the asymptotic behavior or the long-term behavior, behavior after a certain time is in a certain fashion. So we have to understand, therefore, what kind of possible behaviors can be expected from a typical differential equation model, right. Now, one of the and then we are looking at dynamic behavior in the sense that what happens as time changes, and then eventually the asymptotic behavior could be typically static, and it is achieved through a dynamic behavior of long-term evolution of the time, and then eventually it reaches this particular static behavior, right. And so therefore, one of the simplest dynamic behavior is actually static behavior, and I'm going to define that as an equilibrium, right. So this is a very important word that we need to understand in this particular course is the concept of equilibrium. What is an equilibrium? Well, definition is, loosely speaking, if x of t starts at some constant x e, so these are all vectors here, and it will remain at that x e, right. So in other words, if you want me to write the entire sentence, basically x e is an equilibrium, right, if x of 0 is equal to x of e, implies x of t is equal to x sub e for all t greater than or equal to 0. Okay, and we typically represent that as the solution with this equivalency symbol. X of t is equivalent to x of e for all t, right. So that's an equilibrium. Now, one of the obvious things that we can see is basically the derivative of that solution, is 0. Okay. So what does that mean? So that means f of x e is necessarily going to be 0. Okay. So one simple way of defining equilibrium, therefore, is x sub e is equilibrium if and only if f of x of e is equal to 0. Right? So the simplest static behavior or asymptotic behavior that we expect out of a system is actually some equilibrium point, and the equilibrium point happens to be static throughout, right? So if you start there, you remain there. And then how do we find this equilibria? Essentially, solve for this algebraic equation f of x is equal to 0, and then all the points that come out of that particular algebraic equation are equilibria, right? So you can have multiple equilibria and so on and so forth, and we want to understand many times behavior of this equilibria, especially in the asymptotic sense. You may not start in the equilibrium point, you may start somewhere else. We want one of these equilibria perhaps is a desirable one, and in the closed loop system we want to eliminate all other equilibria and then have one single equilibrium point that is of interest to us, and we want to make sure that the system reaches that particular equilibrium, right? So, I mean, I just keep referring to a control problem, though we may not do too many control problems in this particular course, but that's the goal. I mean, we are trying to understand nonlinear systems to see how to take a particular system, from some initial condition to a desired point called equilibrium, right? So, if the basic system had multiple equilibria, then we would ensure that the closed loop system will have a single equilibrium point, and we want to go there. So let's see, what is an example of such an equilibrium point, and then, as usual, I'm going to basically start with scalar linear systems, right? As you can see, in this particular case, Ax equals 0 implies, what are the two possibilities? A is equal to 0, then every x is equilibrium point. Okay, so that's essentially boils down to x dot equals 0, so every point is an equilibrium point. And if you start at that any point there, you would remain there, right? And of course, the other case is A not equal to 0, then xe is equal to 0. So that's the only equilibrium point. So in that sense, for linear systems of this nature x dot equals ax, at the time invariant scalar systems, you only have two possibilities: either everything is an equilibrium point or a single point is an equilibrium point. Okay. What else? Going according to the theme of equilibrium point, suppose if you have something like this. I don't know, some example, right? So here again, for simplicity, I'm going to start assuming a dot a is not equal to 0. Otherwise, things are not so interesting. So in this particular case, the right hand side will be 0 for 3 points: x equals 1, 2, and minus 1. So there are 3 equilibria. Okay. But of course, in general, we can have something like, I don't know, sign of x, right? In this case, we all know that xe is going to be, I'm sure you know this, simply plus or minus n times pi for all n, right? N equals 0, plus or minus 1, and so on and so forth. Okay. So therefore, you can have infinite number of equilibria, right? I mean, you have a case where you have a continuum or an infinite number of equilibria that is a continuum. You can have a case where you have infinite number of so-called discrete equilibria. You can have finite number of equilibria. You can have all kinds of things, right? You can think of basically in this particular case they're equally spaced. In many cases they're not, right? In general, finding equilibria, if some scalar function f of x is there, is not necessarily the easiest thing to do. I mean, we kind of have to solve this particular problem And if you remember, we can think of this as f of x equals 0 can be rewritten as x is equal to f of x plus x, which is essentially a fixed point problem, right? And then we have seen as simple as something like x square is equal to 2. We don't necessarily have a clear-cut algorithm in terms of how to solve for this particular problem. So, even finding equilibria in the case of a general nonlinear system is not always simple, right? Fortunately, most of the practical problems we typically know what kind of equilibrium points we want and things like that, and then we work around that. But in general, if you are trying to analyze a very complex system, then the starting point in terms of understanding the dynamic behavior is as simple as understanding any equilibria. If you don't even know the equilibrium point, then we won't know. And there are some quite interesting problems where it's not easy, right? I mean, there are examples in nature where, say, for example, some large molecules such as proteins fold in a certain manner, and then it's fairly intuitive to understand that they all these points are actually minimizing points of some particular potential energy. So essentially, your model comes from that kind of understanding of energy and behavior of these molecules, but finding those points, those minimum energy points, is not easy because these energy functions are quite non-convex, and then therefore you can have multiple minima, and finding them is very difficult, right? Let alone how they reach each one of these points. So this is somewhat of understanding of our equilibria, and then you can imagine if you have a slightly more complex case, and let's start with the next more difficult case is where you have a linear system, but but a vector case where A is, for simplicity, let's say 2 by 2. Okay, so this boils essentially to solving this equation Ax equals 0, and if you have done linear algebra, you know how I mean, it's not the most difficult thing, but quite subtle things can happen in this particular equation, right? Depending on what kind of equation you have. Suppose you have something like this. Then I mean, this is equivalent to saying x2 is equal to 0, and that's about it. So any point that's of the nature some p comma 0 is an equilibrium point, right? But of course, if A is invertible, then Ax equals 0 if and only if x equals 0. So xe is 0 is the only equilibrium point. Okay, so in that sense, understanding equilibrium points in the case of linear systems is relatively straightforward if we understand a good amount of linear algebra. But just as the case of simple scalar algebraic equation f of x equals 0, if it is a vector one, then not easy, right? I'm going to leave it at that for now. Okay, so we understand that the simplest of the behaviors, right, is equilibrium points, and what are they? They are simply, if you start somewhere, you remain there, right? And these are important because typically we want our control systems to reach to one of these equilibrium points and stay there, right? And in fact, we want more, and then we will see that in the next lecture. If you perturb from one of these equilibrium points, should we go back or remain close to it, or maybe get away as fast as possible? All these are possibilities, and then we will slowly discuss all kinds of such behaviors, and then figure out which ones are desirable, and then how to ensure that that behavior is there in a dynamical system. So let me go back to a simple example that we were talking about. X dot equals x minus 1. I'm going to put x into x minus 1 and x plus 1. Okay? Something similar we have looked at. And let's look at this particular system graphically. Right? So we have equilibrium points at 0 and at 1 and at minus 1. Okay. So let's see what happens to this particular system. Let's say we are somewhere here. Okay. So this corresponds to x greater than 1. We know that if you are at 1 or 0 or minus 1, you start there, you remain there. Right? Okay. So what will happen if you are beyond the region of x greater than 1? So let's go to this particular x dot equation, to the fundamental dynamical equation that we have, and then see what happens. Right? If x is greater than 1, basically x plus 1 is positive, x minus 1 is positive, x is anyway positive. So you have x dot is equal to is positive. Right? So what that means is, if you start somewhere here, you go away from your 1 point. So any point here, you're going to go off like that. Okay. So let's see the other extreme. If you have a case where x is less than minus 1. Again, if x is less than minus 1, all three are negative, right? So 3 negatives are going to have this case of if you start outside of this region, x less than minus 1, you're going to go away, right? So now that leaves us two regions between x between 0 minus minus 1 and 0, and of course you have last case x between 0 and 1. Okay. So but if you are between minus 1 and 0, what will happen? Well, certainly if you are between minus 1 and 0, x plus 1 is positive, x is negative, x minus 1 is what is it? Let's say if you have minus 0.5, and then you'll have minus 0.5 minus 1, it's negative, right? X is anyway negative there. So x is negative, x minus 1 is negative, x plus 1 is positive, so you have a positive condition there. So anywhere you start in this region, you're going to go towards this, right? Perhaps it may look very intuitive. You can go to this region and you will see that basically x is positive here, x minus 1 is negative, whereas x plus 1 is positive. So you will simply get this kind of behavior. Okay. So it's a quite interesting behavior if you start at any of these equilibrium points, right? I mean, anywhere on these equilibrium points, we remain there, right? If you start beyond this 1 point, you go away, and if you start below minus 1, and then you go away. But if you start somewhere between minus 1 and 0, you go towards 0, and then same with starting with between 0 and 1, right? Now I'm going to claim that these points, especially they are trying to reach 0, and that will not happen in a finite amount of time. Why is that? Well, if you reach from this point to this particular point in a finite amount of time, that means you have two possibilities of solution. Excuse me. So, that is, you have a solution that starts at 0 and remains at 0, but you also have a solution that starts somewhere else and then actually reaches 0 and then continue to remain at 0. Now, that contradicts existence of multiple solutions and uniqueness specifically. And how do I know that this particular thing does not have any uniqueness? I mean, actually you go back to the conditions that we have is basically this is a continuously differentiable function, and even between -1 they are perfectly bounded derivatives, and therefore we can actually claim that you cannot have multiple solutions. Okay, so this is quite a simple behavior, quite interesting also, right? Now, instead, if I put, let's say, insert a minus there, okay, what will happen? Well, in that particular case, the equilibrium points will be the same, of course, and the behavior will be exactly reversed. Okay, so if you start outside, you will be reaching towards this 1, and if you start out below -1, then you will be reaching towards -1, and if you start between 0 and 1, you will be going towards -1. If you start between 0 and 1, then you will be going towards 1, right? Okay, and you have this kind of interesting behavior always in scalar systems. We'll maybe take one more example and see what happens. Loosely speaking, for the time being, if I I'm going to introduce a term. If I perturb some solution around 0, you are tending back to 0, right? As I said, we can never reach 0 in finite time, but we are trying to move towards 0, right? So intuitively speaking, we will reach that particular point, and such a behavior is called stable behavior. Okay, we will rigorously define some of these notions later in the course, but for the time being, if you perturb a little bit here, and you can clearly see that you are reaching that particular point. Whereas in this particular case, if you perturb a little bit, either you go off to hopefully infinity, and then or the next equilibrium point in this particular case. So this is what we will call as unstable behavior, right? Unstable behavior. Now the question is whether are these two going to go off to infinity? Well, if they don't, that means they are going to stop at some particular point, and then intuitively speaking, the derivative has to start going to 0, because if they're going to stop there, which means f of x has to be 0, and we know that f of x is actually going to keep on increasing in this particular case, either in the positive or negative sense, and therefore all these solutions are going to go off to infinity. Same here. I mean, in this particular case, everything is a bounded behavior, right? So wherever you start, you're going to go towards 1 or -1, and if you start within -1, and then you just basically get to these two equilibrium points. Of course, in the second example, where we inserted this negative, the 0 is unstable. Okay, the 1 and -1 are stable. Okay, so I want us to appreciate that we didn't really solve anything here, right? That's the whole point. We are not going to solve any ordinary differential equations, but knowing that there is a unique solution, we can use numerical methods to solve these things and things like that, so we can get approximate answers. In this particular case, we may actually solve exactly what the solution is, I don't know, we have to try to see if we can actually solve, but there seems to be a way, because we can use partial, at least we will get some explicit implicit equations that connect x and t, and we can try to attempt at solving this. And then, you know, perhaps you should take that as a homework to see if we can solve this particular differential equation using the differential separable equations approach. Okay, so but we didn't really have to solve anything to conclude so much behavior of this particular two systems, right? One with minus and one without minus, and by just understanding this behavior of this derivative at each of the regions. I mean, scalar systems are quite simple, but vector systems are a bit more complex than this, a lot more complex, I should say. And it's clear that in the first case you have unbounded behavior, in the second case you have all bounded behavior, you have stable points and unstable points, and these are equilibria. And of course, the question is, at least in the scalar case, can we conclude something like this? It seems to be alternating behavior. You have unstable, stable, unstable, and so on. In the second case, you have stable, unstable, stable. Right? So let's explore a couple of more examples, and then of the scalar case, and I'm going to make this example. Okay, x dot equals x minus 1 into x plus 1. In this particular case, 0 is not an equilibrium. It is not necessary. 0 is always an equilibrium, right? So minus 1 and plus 1, and we'll do the same thing as we have done before. If we are beyond 1, then we know that this x dot is going to be positive, so we are going to go off to infinity. Similarly, if you are below minus 1, then you are going to go off to infinity again. What about between minus 1 and 1? Well, you can clearly see that at x equals 0, this is going to give you minus 1. At equals half or something like that, it's going to give minus. So x dot is actually negative between these two numbers, right? I mean, there are multiple ways of concluding that. So basically, what that means is, if you start anywhere in between minus 1 and 1, you have this behavior. Everything is going to converge to minus 1. Okay. Well, what does this tell us? This is clearly unstable. Okay. What about this? Well, at least what we like to have is basically, if I'm perturbing some solution, will I reach back the solution is what we want to define stability as. In that sense, this is unstable, right? So it's not necessary that you have this alternate behavior of unstable and stable. You can have unstable behavior, but it's quite interesting. I mean, it's like somewhere in between. In one case, on one side, you are reaching this particular equilibrium point. In the other case, you are actually blowing up, right? So before we move on to perhaps slightly more complex systems, let's look at this particular case where you have 0, minus pi, plus pi, and so on and so forth. Okay, and it keeps on going. And then if you actually look at between 0 and pi, we all know that it is going to be positive. So we'll have some behavior like this, and we'll have behavior like this, and this is 0, pi, minus pi, and so on. Between minus pi and this thing, then you will have this kind of behavior, and you'll have this kind of behavior, at -3, between -2 pi and 3 pi, and so on and so forth. So, this is an example where you have infinite number of equilibria, and then you will have between every two equilibrium points, you will have a stable behavior, bounded behavior, and each of the alternate equilibrium points are indeed stable. I mean, this is stable, this is stable, this is stable, whereas this one, and this one are unstable, right? You have this kind of pattern of stable, unstable, but you just have to be careful of examples that we have seen earlier, right? So, let us pause for a moment and then go to the next section.